Guys, we're probably working on our last lecture module of this course, so let's celebrate. This is going to be the last one, and not only that, but it's also going to be very quick and very brief, because we're really just focused on one topic for this case, and this topic is going to concern buffers. That's it, people. Just a buffer. What is a buffer? What does it do? And how do I make one in the laboratory? So we're going to talk a little bit about acid and base chemistry theory before we get into buffers, because if you don't understand acids and bases, you're not going to understand what a buffer is or the purpose of a buffer when you begin to use one in the lab. Okay, so some of this stuff you probably have learned in general chemistry. Some of this stuff you might have learned in organic chemistry if you've taken that already, especially the first semester. That's typically how they start out. They like to give you this type of review because they kind of tell you if you don't understand how this works, you don't understand how organic chemistry works. Well, that's a lie. I can actually make it through organic without understanding buffers and acids and bases, but that's kind of their argument. All right, so let's talk about buffers. And I told you before we do, we have to go back to basics, and we're going to have to give you some definitions here. So an acid and a base. These are two things that we're going to find in a laboratory all the time. I mean, every single day it seems like I'm in the lab and I'm using some type of acid or some type of base in order to do a very specific job. So we have to understand the definitions of each one of these. So an acid is properly defined as a proton donor. All right, so a proton donor, what's a proton? A proton is H+. So that means I've got this compound, and this compound is giving off some type of proton, and that proton is typically a hydrogen, and it's kind of just kicking it out to the curb. It doesn't want it anymore. Poor little hydrogen, he's got no home. Boo-hoo-hoo, right? So this molecule doesn't need it. And because it doesn't need it, it's going to kick it to the curb. Imagine you a parent and you have an 18-year-old child that's rebellious, that doesn't want to work, that doesn't want to do any chores, that doesn't want to help out at the house, that mooches off of you and takes everything that you have and everything that you work hard for. What are you going to eventually do? Well, if you're a good parent, you kick it to the curb, right? You're going to say, I don't need you anymore. You serve no purpose here. You're going to have to get out on your own, and you're just going to have to figure out what to do with yourself because you've got no place here anymore. All right, well, that's an acid. You are behaving as an acid if that is what you do. Now, some people will feel very sorry. Some people will feel really sorry for that hydrogen, and it sees it out on the street, maybe nowhere to go, or maybe it's a friend of hydrogen, and it's like, you know what, why don't you just come over to my house and you can crash here for a while? Well, that's the definition of a base. A base is a proton acceptor. So in life, you could be a proton donor or you could be a proton acceptor, depending on your background and your experiences and how big of a heart that you really do have. But you know, those parents that kick their kids to the curb, they've got really big hearts too. That's how they want them to succeed. They got to get out on their own. They got to take up for themselves. So a proton acceptor. Okay, so basically what we're talking about here is that a proton has a positive charge. And if something is a proton acceptor, then it has to accept a positive charge, which means that bases will typically have a negative area somewhere on the molecule. Let's say here is my molecule. Who knows what it is? I don't really care. And let's say a part of this molecule has an area here that is negative. All right, well, that serves as a very good temporary home for a hydrogen because hydrogen is typically positive. And if it looks at these other molecules and it goes, look, there's a vacancy right here. This apartment community, this is where I'm going to crash. I'm going to kind of make it on my own. There's an empty apartment. That's where I'm going to move to. All right, well, that's good news. Hydrogen can find a house. That base can serve as the house for the proton. and that proton can hang out there for a little bit. Now, it's not permanently attached. Most of the time it's not, okay? It just kind of simply hangs out. It stays there for a while until something else maybe persuades it to move on and do other things. Now, let's do a real example using real chemical. Let's say that I take hydrochloric acid in the lab and I add some water to it, and I want to know what happens. All right, well, hydrochloric acid, this is a compound, and it has a proton, and we know that this is an acid because the name gives it away. So hydrochloric acid donates protons. Well, where's the proton coming from? It's right here. There's a hydrogen out in front. All right, so it's going to kick off the hydrogen. And when it does that, what it ends up being is just a poor little chlorine with a negative charge now, right? There's no hydrogen there anymore. There's no positive charge to counteract that negative. And because of that, that chlorine is going to kind of be out there on its own with a negative charge. And that's okay. Sometimes these molecules are big boys, big girls. They can kind of handle it on their own. All right, now the water molecule. I'm going to come down here and draw the water molecule. So water is, if you go back to Vesper theory, water is a bent molecule. And here in the center, we have a pair of electrons and another pair of electrons. And that's what kind of gives it this bent shape. Well, these electrons are negative. So this is going to give water a negative area. This is why we call this a polar molecule, because this is a negative area here in the center, and then these hydrogens, they're partial positives. So we do have a vacancy here. We actually have two vacancies, two pairs of electrons. And that hydrogen can look at this water molecule and says, hey, do you need someone to take up this space? Because if so, I'm looking for a place to live. And the water's going to go, yeah, why not? I've got room for you. If you want to kind of hang out for a while, you're more than welcome to. And this water molecule is going to gain that proton. And it's going to kind of somewhat attach it to that center oxygen. So here's the water molecule. It still has a pair of electrons that it can do something with. And then I'm going to draw a dotted line here, and that dotted line is going to go to another hydrogen. The dotted line basically means it's not permanently attached, like the other two, right? Water to be water has to have the two hydrogens there. Those are permanent bonds. Well, the dash bond just basically means it's a little weaker. This hydrogen can be pulled right back off if it needs to. Well, look, this oxygen now has 3 protons around it, so H3O+, and it's gained some extra positive. It was neutral in the beginning, and then it's gained a positive charge, so therefore it makes that thing completely positive now. So that's the definition between an acid and a base. The acid here is hydrochloric. It gives off the proton. The base in this case is going to be water, and water accepts the proton, and that is by definition a base. And what we have over here are the products. So once chlorine kicks off the hydrogen, we're left with a Cl-. And then once the H2O gains the proton, we are left with an H3O+. Instead of an H2O. Well, we have names for these as well. If this is an acid, then if we just kind of pretend like the left-hand side of this equation didn't happen, and we just look at the products, we'll look at the Cl- here. The Cl-, well, by definition, this could be a base. Because if a proton comes into the picture, maybe that proton will want to kind of hang out with that chlorine for a little bit. And nothing says that chlorine can't make that decision. Chlorine could accept that proton if it needs to. We'll talk about why they would or would not a little bit later. But this could behave as a base. Because of that reason, this name is a conjugate base. So if this is the acid, then this is the conjugate base. All right, so if this is the base, then look, this H3O plus, that's a positive charge. It doesn't like that positive charge. It would prefer if it was neutral. So this H3O plus could make the decision, you know what, this relationship is just not working out. Okay, you're going to have to go. I'm sorry, but you got to go. And that H3O plus will make the decision to kick off a proton. Well, if it kicks off a proton, it is now classified as an acid. It's a proton donor. It's donating it to solution and saying, go find a home somewhere else. But we're going to call this a conjugate. And the reason that we're calling it a conjugate is because it came from the water. It came from somewhere else. These just don't happen naturally or normally. Something's got to provoke it to do it. So that's kind of why we call it a conjugate system. A conjugate base and a conjugate acid. Now, here's the story. Here's the real story. For starters, if you've noticed, I've drawn this arrow a weird way. Most of the time in reactions, you will see an arrow pointed in one direction. That basically means that a reaction takes place, it gives you the products, and the products cannot revert back on itself. And truth be told, this is a one-direction system. This is what we would call a very strong acid. Now, how do I know that? I'll tell you in another video. But this is a strong acid, and strong acids and strong bases lead us to a one-directional arrow, meaning that this reaction cannot revert back on itself. So when it forms the products, these products are formed and it never revert back to the starting reagents. So this chlorine will probably never accept a proton and make HCl again. And this H3O plus system will probably never spit off the hydrogen to make H2O again. And if it does, it's going to be very rare, and it's going to happen in very small amounts. And these small amounts we're just not going to be concerned with. So with the case of strong acids, this is the case. Or strong bases, it is the case. One directional arrow, it forms the products. Once the products are formed, it will not revert back to the starting reagents. It is what it is. Hydrogen is left. Hydrogen will never come back home. Hydrogen will not move back in, and the parents won't stand for it. So those are the products. That's just the way it is now. Sorry, it is what it is. Now, with that said, we do have what we would call weak acids or weak bases. And something like this would be something like acetic acid, CH3COOH. All right? So when these things form products, what happens is that this is an acetic acid, so this is the acid. I know that by the name, acetic acid, right? So that means a proton is going to get released. Well, here's a proton right there. So I'm left with CH3COO minus. All right, well, this H2O can behave as a base. That means it can accept a proton, and what we form is H3O now. And because it was neutral and we gained a positive charge, it is now fully positive. So here we see this positive and negative getting formed again. If this is the acid, then this piece can behave as a base again. So we call this a conjugate base. And if this is the base, then this piece can act as an acid again. So we'll call this a conjugate acid. Again, if this CH3COO was by itself and a proton was nearby, well, why couldn't that proton kind of latch onto that piece? It's negative. Nothing says that it can't, and it could. Well, this H3O plus, well, that's a positive charge. It wants to be neutral. Well, who says that this proton cannot get kicked back off to the curb and says, sorry, you're not working out for me, but you got to go? Well, it could. Nothing is preventing it from doing that. But these are weak acids. Now, how are weak acids different than strong acids and strong bases? Well, that's the arrow. what weak allows us to determine is that this process can happen back and forth. So imagine that you're a parent and you kick out your 18-year-old son and you tell them to go and support themselves. Well, off they go. There you go. CH3COO is now formed. Hydrogen has went off, and hydrogen now has moved into an apartment complex. H3O plus is formed. Well, let's say that that hydrogen there cannot survive, can't pay the rent, can't support themselves. This apartment complex is going to kick them back out. So hydrogen goes back off into the street. That hydrogen could have nowhere to go, and it's going to come back home, and it's going to knock on the door, and it's going to say, you know, I tried this, but I can't make the rent, and you don't want your son to be homeless, do you? You got to let me move back in. And because the CH3COO is very weak-hearted, it goes, oh, I'm so sorry. I shouldn't have ever kicked you out in the first place. Of course, you can move back in. I've got your bedroom ready. I'll fix you breakfast in the morning. So just come on back in and we'll just pretend like none of this ever happened. And hydrogen moves back in and it reforms CH3COOH. That is the definition of a weak acid and a weak base. The weak acids and weak bases will accept the protons or donate the protons all over again, and they will continue to do it over and over and over. So now, how does this relate to buffers? Because that's what this lecture is about, right? Buffers cannot be strong acids or bases. Can't be those. Sorry. That's not the definition of a buffer. So that means I'm going to have to be very particular on what is a strong acid and what is a strong base. We're just going to have to define them. There's a list of them that we're going to have to memorize. Buffers are made of weak acids and weak bases. That's what a buffer is. Weak. And we're going to define this a little bit better in the next video. We're going to go through, look at what strong acids and bases are, and rule those out. And then we're going to kind of discuss why weak acids and bases are a requirement for buffers in order for them to do their job effectively. So that's what we're going to pick up in the next video. I'm going to leave you here. Go take a bathroom break. I've only spent 18 minutes with you, though. And then come back, and we'll pick up with this definition in the next one.